So we have seen about parametric Petri nets and decidability issues in parametric Petri nets. Now we will focus on extending time Petri nets with parameters. So first, let us review a bit classical time Petri nets. So we have normal Petri net, and transitions are annotated with intervals that specify how long the transition should be enabled to be able to fire. So now we can distinguish between enabledness, so we have enough tokens in the input places, and fireability. The transition is enabled, but also it has been enabled for sufficiently long time. An additional constraint that we have here is that when a transition has been enabled in its interval, it can fire as before, but then it cannot wait longer than the upper bound here in the interval. So this here would mean that we have a sequence which is forced for the first two firings of transition. First, we will have to fire T0 at most at date one, and then we could fire T1 at the earliest time at date 2. So now, how do we put parameters in this model? Then we would just have to change the endpoints of the intervals to parameters, and we would get here parameter A and B. And so this is very close to parametric timed automata that we have seen in another sequence. And we can actually relate to the results of parametric timed automata to get some decidability results of bounded time Petri nets. So first we have a structural translation from timed automata to bounded time Petri nets. And this translation, it preserves languages, time languages, which implies that it preserves state reachability. And we have exactly one gadget for each constraint in guards, and timing constant appear explicitly. So what I mean by this is that if in this construction we change the constants by parameters, then nothing changes really. So we can, using this construction, get all the undecidability results from timed automata into bounded parametric time Petri nets. In the other direction, we also have structural transitions from time Petri nets to timed automata. And in the same way as before, we can use them, but this time we will use them to get decidability results. Because of course we can start from our time Petri nets, transform it into a timed automata, and then verify on the timed automaton what we wanted to verify on the time Petri net. So we can do that also for parameters, and we get decidability results for parametric time Petri nets. Now, we have seen before in another sequence that we had to use an abstraction of the state space of parametric timed automata, or timed automata, and we can define exactly the same for parametric time Petri nets, but it's not the one that we will see now, because we have a better, in some sense, that it's a bit coarser, and also it's a bit simpler to use in practice. We have the stateless abstraction from Berthomieux and Menache, and we will now see how this abstraction can be extended to parameters too. So now we have a time Petri net here, and instead of recording in our symbolic state the time elapsed for each transition here, we could say, for example, we start with 0, and then we let time pass, and then we get to 1, and then up to 4, maybe up to 3 here because we have this upper bound. Then we will record the time to fire, like a timer, 5, 4, 3, 2, 1, 0, and 5. So here, initially, we have that T0 must fire in between 1 and 4 time units, and T1 should fire between 2 and 3 time units. So when we want to fire T0, how does it work? We will say, so first T0 should fire before T1, because it's the transition that we have chosen for firing. So we have this constraint, and then we will, since we want to keep this timer behavior, we will say that the new origin, the new reference for timings, time to fires, would be the firing of transition T0. So we make T0 appear here and new variables here, which are the new times to fire. And then we can just eliminate the variables which correspond to disabled transition or to the fire transition, which is disabled. And then finally, by polyhedral operations, we can get a new symbolic constraint. So now, if we want to do the same thing with parameters, then it's just the same, except that we will have parameters. So here, say we have a parameter here and here. Then we can just replace all the constants by parameters, and everything will work the same, except that some constraints on parameters will appear. So here, obviously, if I want to fire this transition, then it means that A was less than B, and actually this comes from these three inequalities. So then everything works as before, except that you see that we will get a polyhedron which is a bit more complex as before, with more variables here, variables for transitions, but also for parameters. And these polyhedra, they have a form which is particular, which we can call parametric zone, but we cannot ensure that there will be a finite number of parametric zones in the execution of a particular time Petri net. So then we can use the same algorithm more or less than with parametric time automata. So for existence reachability, for example, of some state, we have this algorithm that we have seen in another sequence for timed automata, parametric timed automata. But then we can also do inevitability or unavoidability. And it works more or less the same. What we want now is that for every path, we are sure that we will reach eventually a state, a marking here, which is in the set G. So since we want this property for every path, we have here an intersection of the results, but also we have an additional, two additional sets of parameters. So let's start by this one. So det of S means that it's the set of parameters for which there are no outgoing transitions in time Petri net. So it means that the parameters are such that all intervals for outgoing transitions are empty. So these are not good parameters because they create a deadlock. And then we have this part. So if you look at this, you see that this is the reachability condition of the successor, which means the value of the parameter that allow us to take the transition. And we take the complement of this. So what does it mean? It means that we have here a way to cut off the successor. So why do we do that? It's because by doing this, we can sometimes have bigger results than if we just try to make every branch go to the goal. If a branch does not reach the interesting marking, the goal marking, then we can just cut it off. So for instance here, suppose that we have the property that every path should go either here or here. So it seems trivial, but actually to go here we do not have any constraint, but to go here we need that the interval is not empty, so we need that A is greater than 1/2, greater or equal. So if we want to ensure that both paths are possible, then we get the intersection of this and this, and this means that we have A is greater or equal to 1/2. But we could also say, we don't care about this. Let's say that it does not exist in the time Petri net. So we just cut the transition. So we have a Petri net which is which consists only of this part. And then, of course, in this part, we do not have any constraint to reach either P1 or P2, but P2 is not reachable. So how do we cut these? Well, we can just take A is less than 1/2, so this interval is empty, so we cannot take this transition. So for A is less than 1/2, we actually have that we can satisfy the property. So if we do the union of both possibilities, we get A less than 1/2 or greater or equal to 1/2, and we see that actually this property is satisfied for every value of A. So now we have algorithms, semi-algorithms, because termination is not guaranteed, but we can also find a way to guarantee termination, but of course by losing some information in the process. So what we know is that reachability emptiness, so knowing if there is a valuation such that some marking is reachable, is undecidable also for integer parameters, if we restrict ourselves not to rational parameters, but to integer parameters. And we know also that it's undecidable for bounded rational parameters. So say, for example, we say that the parameter is between 1 and 2, or 0 and 1, whatever. So what we can do is combine both restriction and say, let's say we have bounded integer parameters. So now everything is trivial because there are only a finite number of given a bound of integer parameters. And we can actually prove that now the problem becomes p-space complete because we just non-deterministically guess a parameter valuation among a finite number of them. Then we can instantiate the PTA or the parametric time Petri net and solve the problem. We've seen that for Petri nets or for timed automata reachability problem or even TCTL model checking is p-space complete, so p-space here. And then we have a non-deterministic machine that solves the problem in p-space, and we can use Savage's theorem to get that p-space, to get that our problem is actually in p-space and not in p-space, but also in p-space. So what's interesting here that we have now a problem which is decidable. Of course, it's trivially decidable, but then what we will have to do is an efficient way, more efficient than explicitly computing for all the values of the parameters possible what it gives. We will try to do this symbolically and compute all in one step all the values of the parameters that permit to reach some marking. So to do that, we will use integer hull. So what is the integer hull of a polyhedron? That would be the red polyhedron inside the blue one here. So it's actually defined by taking the convex hull of all the integer points inside my polyhedron. So if we use now integer hulls and we incorporate them into our algorithm, then how does it work? Then we just, here, instead of computing the successors of my state class or my zone, then I will just compute the integer hull of this successor. And then we can prove that if the parameters are bounded, then we have a finite number of such polyhedra, and we can prove that the new algorithm is guaranteed to terminate. It's guaranteed to terminate, and it will give exactly the integer parameter evaluations. And then we can do the same for AF. And now we can ask ourselves whether the result that we get, which is actually a union of convex polyhedra, what we know is that the integer points inside those polyhedra, they are the good integer evaluations. What we do not know is whether the other points that we get in these polyhedra are good valuations or not. So basically, for the reachability problem, they are good valuations. So every point that we get inside the polyhedra are good, but it's not true in general for AF, and we will see now a small counterexample. So now we have the same example as before, but we want to, we have the property AF, so all paths permit to mark this place. So of course, for this to be true, we have to cut off this transition. So we have to take A is less than 1/2. But when I take the integer hull of the symbolic state corresponding to the successor by T2, I will get something a bit different. So first, the successor itself, it's if x here is the value of an implicit clock that counts the time from which this transition was enabled. So x should be greater or equal to 1, and we should have 1 is less or equal to 2a. And when I take the integer hull of this, I will get the same thing, but with a is greater or equal to 1. So when I take the complement of this, then of course I will get a is less than 1 and not a is less than 1/2. So all the valuations which are between 1/2 and 1 are not good valuations, but they are in the results of our algorithm. So the problem here is that we have not cut enough states because we have the integer hull of dead is actually included in dead, and not when we take the complements, then we do not remove enough parameter valuations. So to avoid this, what we will do is that we will not use the integer hull by applying to each successor, but we will compute successor as usual and only use the integer hull for convergence. So what we store in our past list and what we check the past list against, it's the integer hulls. If we do that for EF or for AF, then we get a new algorithm which actually gives a dense under approximation containing at least all integer valuations. So we get a bigger result, but in practice it's a bit slower than the previous approach because we have to compute the integer hull from the biggest polyhedron each time instead of starting from already an integer polyhedron with integer vertices. Okay, so if we get back to our example, now we get, of course, in our example that A should be equal less than 1/2 because we have taken the complement of the successor and not of its integer hull. And we can also get a slightly bigger result for EF in this case. So in conclusion, we have time Petri nets and we have extended them with timing parameters by replacing the constants in the intervals by parameters. And then we get the same decidability results for bounded time Petri nets with parameters than for parametric time automata. We have seen how to adapt the semi-algorithms for parametric time automata, and we have in particular explored the possibility of computing only integer parameter valuations or something big enough to contain at least all the integer parameter valuations. And we have seen that for this algorithm we can use state classes, which is really the native abstraction for time Petri nets. And now we can have an approximate synthesis algorithm for time Petri nets with parameters. So to do that in practice, there is a tool which is called Romeo, which works with parametric time Petri nets.